Now, in a vector space, there is an infinite number of elements, and then the reason for that is that if I have at least one element in that vector space, which I know there is at least one, I know that I can multiply that element by any number that I want, any constant. Therefore, since that constant is just a real number, there are an infinite number of elements in that vector space. However, what we want to do is we want to see if we can find a finite number of elements in that vector space that when I take certain combinations of them, linear combinations of them, that we can describe the entire space. That means all infinite vectors based on just that finite set of vectors. So let's actually write our definitions down. Okay. The vectors v1, v2, and so forth onto vk are said to span V, which is our vector space, if every vector in V can be written as a linear combination of the v1, v2, v3. So now we've actually written it down. So if I have vectors v1 through vk, let's say 6 of them, and if any linear, excuse me, about to sneeze. If any combination of those vectors, they don't have to all be included, some of the constants can be 0, but if some combination of those vectors can represent every single vector in that vector space, then we say that that set of vectors actually spans the vector space. Okay, now let's list the procedure to check to see if a set of vectors actually spans a vector space. Procedure to check if a set of vectors spans a vector space. So VS just for vector space. So let's see, you know what, let's leave it as blue for right now. Choose an arbitrary vector v in the vector space. So when you're given a vector space, just choose some arbitrary vector. So if you're given, let's say, 4 space, R4, then just choose the random vector A, B, C, D, or you can call it X, Y, Z, T, just some random vector, and label it with some. And 2, okay. Determine if V is a linear combination of the given vectors. So this is just basically an application of the definition, which is what definitions are all about. Let me just take a quick second to talk about definitions real quickly. Often in mathematics, you begin with definitions. They are a basic element. And then we use those definitions to start to create theorems, and then we sort of build from there, build our way up from the bottom, if you will. If you find that you've lost your way in mathematics, more often than not, you want to go back to your definitions. 90% of the time, the problem is something is either missing from a definition, or there is a definition that the student hasn't quite wrapped his mind fully around. Again, mathematics is very, very precise. It says exactly what it wants to say, no more and no less. Okay, determine if V is a linear combination of the given vectors. So adjust the definition. If so, if it is a linear combination, then yes, the vectors actually span the vector space. If not, if there is no way to form a linear combination, then no. Okay. So again, when you're forming a linear combination, you're taking a constant, multiplying it by a bunch of vectors, and setting it equal to some, in this case, an arbitrary constant. So once again, we're going to investigate a linear system. Linear systems are ubiquitous in linear algebra. Okay. So let's start with an example here. Let's